BayLISA is held on the third Thursday of every month, and its meetings are open to the public. We are a membership organization, so we encourage people to join, but it's not required. Membership fees enable us to pay for various expenses like the website, Meetup.com fees, meeting refreshments, and travel expenses for speakers out of the area, so that we continue to bring you the best speakers with relevant and interesting topics. Individual membership is $45 a year. Corporate membership is $500 a year. If you or your organization would like to become a member, please speak with our treasurer, Guy Purcell, after the meeting. BayLISA would like to again thank PayPal for providing the space to hold our meetups. Please be respectful of the facilities and PayPal employees, and please remember to clean up after yourself. The Wi-Fi information is on the board there for those who haven't seen it yet. PayPal guest and safe payments. The BayLISA board itself is always looking for new members. If you enjoy these talks, we encourage you to give back to the community and help. It's not hard work, but the more hands make the lifting easier. The board meets for dinner on the first Tuesday of the month to discuss topics and speakers and plans for general meetings. More important is finding speakers, so even if you don't have time to personally come and help, we are always looking for ideas for people to speak. If you want to contribute or have ideas for subjects or talks, please find myself or one of the board members, or feel free to drop us a message on the Meetup site. We typically reserve some time for announcements. To start us off, are there any BayLISA board members who have announcements? No? Is there anyone in the audience who has like a general announcement, something you know is going on that you're interested in sharing?
Thank you for the great beer.
Oh, that's PayPal.
Mike Wong.
Mike Wong is our beer master. Thank you, Mike. Okay. We'd like to keep you informed of upcoming interesting events going on in the Bay Area. Next week is the Silicon Valley Blockchain Conference, a two-day event held in San Jose Convention Center with talks, exhibits, and demos on all things blockchain. You can purchase tickets on the website, or if you ping me, there's a Google form you can fill out to try to get a free ticket. On July 11th, the San Francisco Google Developer Group will have a meetup on visualizing data with Data Studio, Google's next-gen business intelligence and visualization platform, plus a talk on applying neural nets to do object detection inside video games. The Storage Developer Conference is being held in Santa Clara this September 24th to 27th. 4 days of highly focused tracks on bringing storage professionals of all levels together to learn about new storage developments, best practices, products, and services. And then finally, the California Extreme 2018 will be held. It's a game convention. Pay for the day. It's all the games you can play. Tons of fun. We typically have job announcements, so if there's anybody who's looking for a job or who has a job announcement to make, now's the time you can get up and tell us. Everybody has a job? Nobody's looking for a job?
I'm looking for a job.
Oh, what job are you looking for?
I do, I'm BayLISA, so I'm a system administrator, but with the InfoSec focus. So,
Okay, so if anybody out there knows a job? Excellent. The events I mentioned, those are what the QR codes on the doors are, so if you're interested in any of them, you can scan them on the way out. Before we really get started, we ask you to please check your phones and put them on silent or vibrate. Many of us are on on-call rotations, and we understand if you get paged, but please, if you have to take a call, minimize the disruption and step outside. So tonight we have two talks, one from a fan developer of Plan9, the other from the founder and tech lead of Evolute. Ah, good. As I said, for Plan9, we have a fan and contributor Plan9, Plan9, that's that movie, that one worst movie ever, right? Yeah. No, but that's not the talk. We're having a talk on the operating system. It's Plan9 from Bell Labs, not our space. This was the operating system that was contributed and written by many of the people who brought us Unix and C, so it's very interesting technology. And so please help me welcome Ori Barnstein with this talk, Not Dead, Just Resting, Plan9 in 2018.
Hey, so I'm here to talk about Plan9, which, as I say, is not entirely dead, but it's not the most lively of systems at the moment. This talk is actually presented on Plan9, although jumping through a couple of hoops. Turns out that the driver support isn't all there. Okay, so to start off, are there any questions? I'm going to ask everyone to ask questions through the talk rather than, don't feel like you have to hold it all to the end. I'd rather be interrupted and answer something, clarify, make sure that I haven't glossed over something important. So feel free to stop me at any time and ask. Okay, so yes, I do have a working Plan9 laptop. It's right over there. Yes, there's probably something wrong with me for actually having one. Basically, feel free to come up to me after the talks are done. I will be happy to show you around, poke at some more interesting stuff, explain what exactly some of the things I do are doing, how things work, and so on. Okay, so Plan9 is probably not a system you want to use. Disclaimer right up front. I will be talking about it in gushing terms, but it's also probably going to, if you try to run it as a real system, you're going to run into problems. Yes?
How old is Plan9?
I will get to that soon. It was mid-late 80s. That's when it was first started, and it died in 2015. Okay, so
Are you running natively in the hardware?
that one is running natively in the hardware. This one is running OpenBSD, and I'm remoted into it because the display drivers don't do external monitors. Okay, so
I think that needs an applause, right? Because that's a hack that makes sure this presentation continues. So let's give him a round of applause for getting that hack. Yeah. Thank you.
I did have backups. I'm reckless, not stupid. Okay, so many people, when they first try to use Plan9, will basically ask, why isn't it Unix? Why doesn't it do X, Y, Z the same way as Unix does? Because it is kind of Unixy. So, sorry, but Plan9 doesn't use X11. It uses Rio, it uses DevDraw, it does its own Windows system. This is the actual Emacs man page. I deleted a few lines for brevity, but if I run man Emacs, this will show up. There is a VI man page. VI is the MIPS emulator. So many programs that you expect to be there on a Unix system will not be there. Many programs that you're used to using will not be there. Not having X11 means that even if you did port them, if they had a graphical interface, they would not work. There are many little things that you will run into if you try to use it as your main system. Unless you're a stubborn idiot like me, you'll want to stick to Unix, Windows, Mac OS, something reasonable. So, with that warning out of the way, let me explain what Plan9 actually is. It's an operating system that came from Bell Labs. It was written, again, by the same team that created Unix, so Ken Thompson. Dennis Searchy, I believe at that point was a manager, but he was involved in the creation. Rob Pike, who is more famous these days for creating Go, was also the lead, one of the leads on Plan9. It basically had it has the full Bell Labs heritage. It's a Unix-inspired, minimalist, distributed, graphical, text-oriented research operating system. Okay, now that I've spat out the buzzwords, I should probably define exactly what I mean by that, especially since some of these might not mean exactly what you think. So, it's a minimalist system. Minimalist system means it's got a small number of moving parts, it's got a small number of design patterns, it's got a small number of lines of code, and actually, let me just, sorry, scroll that. I'm going to run this build in the background, and when you see things stop scrolling, you'll know it's done. It should take about a minute to rebuild the entire system from source, including the kernel, the compilers, the graphical interface, everything. It might be a little bit slower because the output's going over the network, and I think that's going to be the bottleneck. So,
Waiting all day for Jen.
yeah. So, minimalist. It's Unix inspired. So, if you're using Unix, Plan9 will probably live somewhere in the uncanny valley. You'll walk up to it, type some commands, and they'll be similar to Unix, but somehow different. You know, kind of like if your mom went out to the plastic surgeon, got a facelift, and came back. It's familiar, but not exactly right. So there's a lot of things that will be the same, like it's got a hierarchical namespace, it's got ls, it's got cat, it's got grep, but there are many things that are different. For example, mount doesn't actually mount a device. It mounts a file descriptor or a socket.
Does it have pipes?
It does have pipes. Those are done through a file system. Yeah, so it's a distributed system. So it's distributed, but not in the sense that many of you people will be familiar with not in the sense that many people today will use distributed system. It's distributed in the sense that you have transparent access to all of your network devices and all of your devices from across the entire network. So it's easy to construct a namespace for a program which has this laptop's mouse and keyboard, that laptop's webcam, my server over there's disk drive, and so on, all put together and accessible for one program transparently. But you don't get, say, a single system image where one program will transparently move across nodes. And while you could write a distributed algorithm that does a map reduce across multiple hundreds of nodes in the cluster, Plan9 doesn't do that much to help you with it. It will let you you can obviously do it because you have the ability to spin up things and run programs on different nodes. They can communicate with each other because there's networking, but there's no special magic sauce that makes it happen transparently. It's graphical, so that means that it's actually designed graphics first. It's probably not going to be usable at all without a graphical output. The console doesn't have scroll back. It doesn't have the ability to go through command history. That's delegated to the Windows system. Your text is all texty, so you can do, for example, if I wanted to create a new window, I could type in a button, click it, and I have a new text editing window. The buttons don't have to go in the top bar, by the way. I'm done with this window, so I'm killing it. That's kind of graphical, but it's also text-oriented. So you're using graphics in a 2D environment, but it's all to manipulate text. Actually, by the way, the build is done. So you can go back into your scroll back and edit the text. Hit send, and now you've got the output here. I want to cat this file. Let me just send that, and the output's there. So I'm taking the command history, editing it, turning it into commands, dumping it to the end of my input buffer. Again, graphical, you can't really do that without something vaguely graphical, but it's text-oriented. And it's a research operating system. So that means it was built by programmers, for programmers. It's kind of designed to be practical because they were using it as their day-to-day system. But it's also designed, for example, to make it really easy to hack on. It comes with a program called Source that you highlight the text and, didn't quite work. I'm plumbing it to a different editor. If I had a different editor open here, Sam, I'd be able to, run that command. It would pop up in my other editor, and I'd have the source code to ls popped up and open. It's got some other surface differences. For example, as I mentioned and hinted at, the GUI isn't X11, it's Rio and DevDraw. Yep.
There's no undo stack?
There is an undo stack.
What?
Well, in the editor. I just hit the undo button. But, okay, so there's the shell. The shell isn't a Bourne-like shell, it's RC. I assume RC stands for run commands. Which has a lot of the Bourne shell warts cleaned up. So, for example, you can actually have variables with spaces in the name and not have them accidentally turned into a list. The shell has lists. The editors are Sam and Acme. I'm using Acme to do the presentation. For most editing, I actually use Sam, but Acme is a lot easier to script for creating these slide plus, slide minus buttons. Passwords are managed through Factotum, which you can think of as kind of a combination of LastPass and LDAP. So it'll do passwords for all your protocols. SSH is done through that. HTTPS is done through that. Whatever security negotiation your programs need to do, they hand that off to Factotum. So any program that needs to authenticate on any protocol, just ask Factotum, hey, can you authenticate on this for me? And then Factotum kind of goes, yep, let me talk to the other guy for you, do the authentication, and okay, here's the authenticated file descriptor. You can do whatever you want with it now. X11 becomes DevDraw. NFS becomes ExportFS. ExportFS is actually a lot more powerful than NFS because, well, I'll get into that. And Plan9 is also the source of many well-known innovations. So UTF-8 was actually invented for Plan9. UTF-8 were basically, the short summary of the story there was that I believe Rob Pike and Ken Thompson were unhappy with one of the standards that the standards body, ITU, I don't remember, one of the standards bodies was pushing. Went to the diner, scribbled out a better encoding on a napkin, implemented in Plan9 in about a week, shipped it, and went, hey guys, we've got something better. Do you want to use it? They went, yep, we should use that. And the first time in history where a better implementation and a better design won out over a worse one. Okay, I'm a little bit bitter, but yeah. Plan9 is also one of the place where rfork on FreeBSD or clone on Linux was inspired. So Plan9, when you create a process, you rfork it instead of forking. Rfork allows you to share some resources. So if you want to create a thread is just a program which shares its heap and it's, actually on Plan9 it doesn't even share the stack. But it shares its various attributes with the process that created it. On Linux, that's how threads are created. On FreeBSD, I think it's actually not usually done through rfork, but that's where it came from. The /proc file system also came from Plan9. Actually, technically it came from V10 Unix, but it was implemented in Plan9 extended there. It's the first place you could actually do things like debug through /proc. So ptrace is gone, /proc is your debugger interface, and you can do that. Porter-Duff compositing is another place that Plan9 innovated. I don't know how many people here are graphics people, so let's just say that if you have alpha blended transparency, that's Porter-Duff compositing. It came in Plan9. It directly inspired what's implemented in X11. So if you read the paper on Xrender, it cites Plan9 directly. And namespaces. So the idea behind Docker's process sort of isolation also was pioneered in Plan9. So Plan9 is now dead. The last commit on the official Bell Labs site happened in 2015 when Jeff decided to go and go on display at Google like all the XBell Labs people. So who's left? Well, there are a few people kind of hacking on it. Some of the statuses here are fuzzy and reconstructed from what I can see on the internet, so it may be incomplete. But there are a few main forks. 9 Legacy, 9 Atom, Harvey, and 9 Front. There are probably a few more. There may be more forks than actual users, who knows? So there's 9 Legacy. 9 Legacy claims it's not a fork. It's basically, people keep on patching Plan9. Bell Labs is dead, the patches accumulate. These guys collect it. They have a repo called Plan9 Contrib, which puts it all together, or they just have patches on their website, which you can apply at will. And it's kind of taking the old traditional Plan9 without any major changes, adding a few tweaks to make it slightly more usable, fix bugs, and basically give you the same old thing. There's 9 Atom, which is basically the same thing as the Bell Labs version, but with more hardware support. As far as I can tell, the site is still up, but there haven't really been any major public updates recently, so it may also be dead. There's Harvey, which is basically they took the Plan9 source code, forked it. They've been switching over from the Plan9 native compilers to GCC. They've been rewriting the POSIX emulation layer to actually work. They've been pushing for trying to get X11 actually working there, rewriting the UI to look more commonplace and traditional, something that Unix people will be comfortable with. And I mean, it's kind of cool that they're doing it. I'm ambivalent because I've already got Unix. I don't need a second Unix. And there's 9 Front. 9 Front's the fork that I'm currently using. And it's written by crazy people. They've got an interesting sense of humor. So this may or may, why did it decide it didn't want to do that? Let me just show you the image. Reflexes. It'll take a little bit of time to load because networking. So, for those of you who may be aware, so it's written, the main developers are German. So German engineering, that's the Hindenburg. They've got a sense of humor. It's an interesting one. It may not be for everyone. These people manage to do crazy stuff. Like this stuff, okay, I'm half trolling, although I have heard reports that it may be true. I'm running Plan9 natively on that laptop. It's got graphics drivers, it's got Wi-Fi that's working, it's got, so that laptop doesn't have NVMe, but if I put an NVMe drive into it, that would work. Plan9's got, okay, not great hardware support because it's a tiny community, but there is a surprisingly good chance that if you take it, toss it on a machine, with a little bit of care and a little bit of PCI to ID diddling, that there's a chance you can get it working and running with good hardware support. Like the native Intel graphics drivers go up to Haswell. And they've actually written native Intel graphics drivers. You don't necessarily have to use Visa. Yes?
So given that Plan9 is no more, what did you learn personally or about life or about operating systems by using it?
I'll get to that soon. But it's not entirely dead. As I said, there are forks. The official main repo is dead, or the main development from Bell Labs is dead, but 9 Front is actually pretty alive. You're getting several commits a week, several hardware updates a week. It runs on fairly recent hardware. As I said, it's got native Wi-Fi drivers, native Intel graphics. It's got virtualization. I can run OpenBSD on this thing. I can run Windows on this thing, although I think it can't. It can only handle older versions. And I can run Linux on this. It's really slow, but if in a pinch, if I need to, I can spin up an OpenBSD virtual machine. And let me close this thing. Q. Why is this screwy? Oh, networking issues. I haven't set up my namespace right. I can show you this thing running OpenBSD after the talk. But it will boot up OpenBSD. And just for the sake of humor, they use Matt Damon to forward packets, do transparent ARP proxying for the Wi-Fi.
That's awesome.
Yeah. So NVMe, as I said, their support. And I also said that Synap is crazy. This was his weekend project. He went from 0 to working NVMe drive in a weekend in virtualization, tested it, fixed a couple of minor bugs, I think an issue with the doorbell registers, and had working NVMe. I ran it. I found one bug in the drive not conforming to the spec. These people are nuts. IG wrote a new TTF rendering engine. Basically working, rendering fancy stuff. I'm going to work around the issue of PNGs PNGs not wanting to load in my presentation, so. Sorry. Nothing ever goes perfectly. That would be crazy.
The joys of Plan9.
Yeah. As I said, it's not a practical system. I'll show you the text here we go. So, here we go. Font layout with a completely new TTF rendering engine, written about 3,000 lines of code, doing layout and whatever else. It's also got a snapshot and file system. So this has actually been in Bell Lab, in the Plan9 world, since the beginning. You get file system snapshots the entire, through, you can actually see this is a fairly recent installation. I can go through and look at all the old versions of my files. And this has been in there since the 80s, early 90s, somewhere around there. Wow. But all of this is missing the point. So to your question, you have this in Unix, it's working. Why bother? Well, Plan9 also does a few things really nicely that you can't do in Unix. And the essence of Plan9 comes from having 9P, which is their network file system protocol, and namespaces. So 9P. This is the entire list of messages in 9P. You've got the T messages, which are the transmit, the R messages for receive. You have the usual, so these can be split broadly into 3 different groups. The version negotiation, the file hierarchy manipulation, and the read and write calls. And there's also namespaces. So you can basically take any set of names in the Plan9 world and kind of interpose them or shuffle them around and build a private namespace for every process. So each window here is running in its own namespace. I can have one window importing some devices from one machine, another window importing different devices from a different machine, and the two windows don't interact with each other, which lets you do some very powerful things. But it's not about 9P. 9P is a nice mechanism. It's implementable by humans, which is a giant bonus. But it's about unified mechanisms and interposability. So you can get some of this or a sense of this. If you've ever worked at Google, everything is gRPC, except not everything, because anything local still goes through the usual system call and mmap interface. So if you want to change how you talk to the hardware, well, now you're stuck because it's not gRPC and you have different stuff. But you get a taste of it through what happens at Google with its pervasive use of a single set of RPCs and approach to system design. And this is really the source of power. So again, gRPC, it has its issues, but it's awesome. Just the usual thing. And namespaces, again, they kind of are the inspiration behind what gave you the ability to make Docker. Docker has its issues, but it also lets you kind of bundle things up, replace what names you're using, and really just kind of give a different view of the same system through the same APIs. So again, it's not entirely the same. It doesn't have the same uniformity that you have under Plan9, but it's there and you kind of get a sort of hint at what the Plan9 world can give you through them. So for example, there's the /net namespace, or the /net hierarchy. This is just kind of listing some of what the files you'll find in /net, which is, to put it in a way, Plan9's replacement for sockets. Again, everything is 9p. Everything is done through file system hierarchies. There is no way to communicate to the system without using 9p, other than exec. And I guess if you squint hard enough and look at the hacks that they use to make graphics work, there's some way of mapping the graphics card registers in through a special seg attach, but that's kind of off to the side and concessions to the real world that a research operating system kind of grudgingly made. But their /net namespace basically has a whole bunch of files in there, which means that you can actually connect to it and mess with it through a shell script. This is actually taken from an IRC client, and this is how you would, with raw file calls, create a connection to an IRC server. So what this does is, here at the bottom, we have the dial using the /net hierarchy. You can use anything you want here, but /net is kind of is the conventional one, conventional place you put your network stack. You give it the address, you give it the command that you want to run after having the, after building the namespace. So then you have the dial function. The dial function takes the address that you're trying to connect to, pipes it to NDBCS query on the network stacks connection server. So that basically you tell it, hey, can you do DNS for me? Or can you tell me how to connect to this system? You do a little bit of munging on the output because it's not in a perfect format. And then you echo it to the netdial command, which actually echoes it, which actually manipulates the /net namespace into, into actually creating the connection. So now that you have the connection by piping into the control file, okay, let me step back a bit. First, you basically take the connection file and say, you pipe that into the control file, and that control file will basically tell you, okay, here's the connection ID. Where do I read? This is where I read and write data from. Then once you have the data file, you know which data file you're reading and writing from. You can set up the pipes, input from data, output to data, and run the command with standard in, standard out connected to your network. Kind of cool. But wait, there's more. What if I don't want to use my network stack? What if that machine over there has a better network stack? What if there's a firewall in the way and all I have is a 9p connection to a different machine? What if I want a proxy? Well, all I have to do is say, hey, let me import the remote machine's network stack, put it on top of mine, and now all of my calls to the file system go through someone else's network stack. Goodbye to NAT. We don't need to do network protocol level hacks. It just falls out of namespaces. Goodbye to a whole bunch of other hacks like that. It just falls out of namespaces. This is kind of applied all the way through the Plan9 system. For example, right now I'm using graphical mode. Graphics go through DevDraw. But DevDraw is just a name in a namespace. What happens with the way the Windows system works is that the Windows system runs on the kernel's DevDraw. The kernel's DevDraw is exactly the same as what every program uses. If I wanted to boot and I started up and I had a graphical console, which I do, I would be able to run any graphical program directly on that DevDraw, and it would just work. The Windows system basically takes that DevDraw, slices up chunks of it, and says, here's your smaller DevDraw, let me put it into this program, into your namespace. And the program then runs on top of the Windows system's DevDraw, which proxies the kernel's DevDraw. These DevDraws are all exactly the same as far as the program can see, which means if I wanted to, I could create a new window and run my Windows system inside it. And now I've got a nested Windows system that doesn't know it's nested. So there's a lot of cool stuff you can do with this. Dev mouse and keyboard work the same way. And hell, even this presentation is working this way. So Acme is the text editor, and it serves itself up as a file system. I can show the slide plus and slide minus scripts, but they're not too interesting. The real cool stuff happens in the slide program. There's how I switch slides. All I'm doing is going to this Windows private namespace, saying echo the name. So the way you'd use the slide program is slide name. There should be an N in there. I should learn how to type, but whatever. So you say slide name. So what it does is it switches the window name. It says, okay, let's put this file name in here, clear out the current window, and then read the new file name in. Each slide is its own text file, and I'm swapping through it writing to a file server. I don't want to save my changes, so screw you. Okay. So all of this is kind of what feeds into putting together a Plan9 network. So Plan9 network is usually composed of 4 different components: the terminal, the CPU server, the file server, and the auth server. You can have more than one of each, but those are the main components. And you can also have more than one component running on a single machine. Okay, so the terminal is basically a half-dumb terminal with local device access. The way I'm remoting into this machine is actually I'm using it as a terminal. There's not much state on it. You can have some state. It'll export its devices to the other systems you use, but it's basically you flick it off, you walk away, there's nothing there. But you can do computing on it and so on. There's a CPU server. CPU servers are basically a beefy server. You kind of SSH into it, but because of the distributed nature of the system, you can put whatever you want into that program's namespace, including your local devices, and typically you do have all your local devices in there. And yeah, they run programs. They don't do migration, they don't do any of the fancy distributed stuff, but they work that way. File servers store your data. They have your snapshotting capability that I showed off. Yeah, and auth servers, which are actually kind of cool. As I said, they're kind of the way Plan9 authentication works is halfway between LastPass, SSH agent, and LDAP. So user accounts go on there, but it also stores all your passwords, or it can store all your passwords and keys for all of your various accounts. I can SSH into another machine. The SSH program will ask Factotum, hey, can you do the SSH key negotiation for me? It does a key negotiation. It gives you an authenticated system, and you move on. And yeah, I kind of went over that already. And so generally, Plan9 composes into a network through gluing together namespaces on multiple machines. And that kind of gives you seamless access to remote resources, which all falls out of the system. So if there's one thing I want to take you guys to take away from this talk, it's not that Plan9 is awesome. It is, but it's also terrible. It's kind of clunky. You don't get a browser, you don't get anything modern. It's going to be a pain in the ass to use in the modern world. But I want you to take away the idea of a unified API and unified way of doing things. So the ability to actually say, hey, there is this way to do it, and there's only this way to do it, and you can kind of replace these things is really the source of power in Plan9, and it's also the source of power in systems that you can implement. It may not happen as deeply, but it's also, but it may but it does, but you can do it. It's better to have one protocol that fits all your use cases, even if it doesn't fit them perfectly, than it is to have 10 different protocols, 9 of which are completely different from each other. So if I have time, I can actually show you how RCPU works. So RCPU is what you use to log into a remote system. It's a shell script. It's 90 lines of code. It's basically taking your local system and telling it to export and manipulate the namespace to log into another system. This login into that system is done through RCPU running in a user space kind of kernel-ish environment. So draw term basically emulates enough of Plan9 to run RCPU to log into another system. It's a really weird way of doing VNC, but it works. Okay, so starting at the bottom, by the way, this is everything. What you're doing is you're saying, take the, connect to the other host with your client program and redirect your standard in to FD10, standard out to FD11, standard error to FD12. So this is just so that you don't clobber things or clobber your file descriptors. So connect basically connects to the remote system and has it run the export command. What you end up doing is exporting the on your local system, what you do is you say export my/dev and mount it onto the remote system's mount term. Mount term is basically the conventional place where you put, when you log into a CPU server, mount term is where your terminal's devices go so that you can bind them into another place. The server starts by taking the mount term devcons and binding it to your devcons. So your console is now your local system console. So when a program runs on the remote system, it writes out to your local system. Then you can then there's a little bit of dance to forward signals over the network. So if I hit delete or Control C for the Unix people, then that basically makes the program here gets the note, sends it to the other system, and forwards it on. And you can kill programs remotely. Yay! Same happens with dev draw, dev keyboard, dev mouse. So now you've got a namespace on your remote system where the local devices are kind of bound over the remote system's hardware. If you want, you can bind more of it in your profile, but this is enough. That's all you really need to do to get remote login working. There's a little bit of extra glue around authentication and user management, so obviously it would be bad if anyone could CPU into your machine and run programs. I think there are some people paid very highly to prevent that sort of thing. So that's where the auth server comes in. We talk to that thing before we allow anyone to CPU in, but this is really the essence of how things work. And all of remote login, all of the replacement for VNC or Windows Remote Desktop is a 90-line shell script, and it's more powerful and more flexible and more general than anything you'll find outside of Plan9. So that's about it.
How does the address networking part work?
How does what?
You mentioned the address. How does the address being come into play when you have multiple machines? So as I said, it's not distributed in the usual multiple machine sense. You have to log into a specific machine.
And you can put multiple things into your namespace from different machines. So that's done with rimport or export fs. So actually, so come on, plum for me. Whatever. Let's see if that one works. Nope. Maybe I got it the wrong man section. Okay, import 4. So, fuck it. Import, I don't remember where I don't know why it's not plumbing for me. I think I may have not mounted the plumber. Oh, shit, of course, I didn't mount the plumber. So, remote login by default doesn't actually start all, by default, CPU doesn't start all the services that you would expect. So, Plan9 has this cool feature called the plumber, which I didn't talk about, and I guess I'm going to now because it didn't work. The plumber basically lets you say, here's this text, figure out what program can handle that text, and open it with that program. So if I have rimport in the thing and I right-click on it, it sends it to the plumber goes, oh, that's a man page. Okay, let me open it. So rimport basically is equivalent to a CPU, except instead of giving you a window in a namespace, it takes the resources from a remote system and imports them to your local system. Yeah.
So every OS has lots of vulnerabilities at the kernel.
Yes.
About Plan9.
Yes.
Is there anything about Plan9? Is there anything about Plan9 that would make it easier to fix those problems?
So the code base is a lot smaller, easier to understand. You can definitely actually read through the kernel source and understand it and make sense of it. The fact that you're using factotum is kind of a benefit because all of the key material is sitting in one auth server off to the side that if you're security conscious and not super cheap, will run only factotum, have the keys written NVRAM, and if factotum and the kernel are mostly secure, you don't have a whole bunch of other services that are easy to break into, which can compromise the key material.
Okay, but the kernel itself is just a monolith. The
Yeah.
vulnerability anywhere gets you everything.
Yes. There's nothing special. I don't think Plan9 has particularly amazing security properties, and given the number of eyeballs, it probably has more vulnerabilities than many other systems. Yep.
Yeah, just to follow that up as a comment, it was written back in the 80s, remember?
Yeah.
When everybody was collaborating
But
and
so was
everybody was
Kiko.
on the same page and all,
Yeah.
everything was groovy.
No,
Yeah.
Kikos was written about the late 70s, and it has a kernel that's not a monolith. So each component that have controls within the kernel about what they talk about.
Yeah. So one thing that I should point out is that due to the way that Plan9 is designed, the kernel is actually probably smaller than many microkernels. So, for example, my file system's in user space, my auth server is in user space. Theoretically, they put the network stack back in the kernel because they wanted to improve performance and reduce context switches. But it used to be in user space and it could be moved back out transparently. So I'm going to pull up the, I think that's the file name. No, maybe not.
That's right.
But basically, the way that kernel drivers are written, they're also serving up their data over a pseudo Plan9 interface. So it's trivial to pull them out into user space and split things up. So again, minimalism, it gives you a kind of smaller attack surface. And while, yeah, Plan9's security wasn't the #1 priority, they did consider it. Factotum actually has a number of features and kernel modifications to support it being secure. So for example, you can set memory as non-pageable, so specifically so that Factotum will not page secrets to disk, things like that. Yes.
So this was like written like 30 years ago, so if you had an 8 megabyte of RAM, you were rolling fat. So what were they thinking? I mean, the problems they were trying to solve, is it of a distributed kind of system? That machine's fat, mine's skinny, and no security, but they're at Bell Labs.
No, there is definitely security. They do, so authentication is actually baked in. They have a lot of really interesting ideas around security, but I didn't go into that. Anyways, yeah, they were definitely thinking that machine's fat, that machine's skinny, but they were also thinking, you know, it's kind of nice to be able to just sit down in front of any machine and start using it, logging into a central system and using the resources from all over the network. And they were also definitely thinking along the lines of, you know, what if we could just kind of put together a system out that was made of a whole bunch of nodes.
Renewal Linux was done the most minimal
Yeah, you got 4K already.
But
Yeah.
the idea here is, what if you want to go back and retry it again, but try not to bring along the baggage?
Yeah. So that's why Plan9, part of why Plan9 is not Unix. Yeah. So yeah, if you're using a single node on a Plan9 network, yeah, there are definitely advantages, but you're also kind of missing the point. Yes.
Okay, a small factoid. Some of you guys might remember the FreeBSD, FreeNAS presentation done by BayLISA. And when they rebooted and did FreeNAS 10, they actually used 9P in FreeNAS 10, which was FreeNAS X. And that was, I think, for their Beehive and orchestration stuff they did on the back end. I'm not quite sure why they chose 9P, but it brings it into the forefront because, you know, something that's you could run on your home system and actually use right now.
Yeah.
And on that same note, I wanted to ask you, do you see a place for maybe like IoT for Plan9 that, you know, I'm thinking like what are real world use cases possibly that you could see?
So there are places that it would be kind of cool to use it, but realistically, I can't see a company doing it just because the pool of talent is way too small. I think that Plan9 is probably going to stay as a hobbyist system just because of that sort of thing. There are a lot of things that it would be kind of cool for. So sensor networks, especially if, as the 9front folks are planning on, they're looking at doing 9P 2020 or some other slightly more cynical, more bitter name for it. But they're looking at, so Plan9 9P, as I said, it's not perfect, it's not, and if you focus on the specifics of 9P, you're missing the point. Some of the problems it has are around latency. So on a high latency network, you have a lot of round trips that need to happen that shouldn't. There's definitely a desire to fix that. That'll kind of hamper it for IoT devices. At the same time, it would be really nice to have the same sort of unified namespace management around, say, sensor networks. So, I don't know.
Yeah, low time, low latency, skew time, because the nature of this is message passing. Very short amount of code length in these things to begin with. So that's one of the advantages of it there.
Yep.
It was intended primarily for a bunch of theoretical computer scientists to do theoretical computer science stuff with. And then maybe afterwards it might get interesting.
Yeah, although to be fair, the Bell Labs Computer Research Group was surprisingly practical. And they do have support for async, or not async, but the kernel driver dev mount does do a whole bunch of pipelining and interesting stuff to lower latency, but the protocol doesn't quite support it. A specific problem would involve short reads. So right now, what you do is you give 9P a read this much data. It comes back with, okay, here's this much shorter length of data. And you can't really pipeline that very easily without a whole bunch of song and dance around trying to fill in holes, because when you say read, it says you're giving it the offset to read from. A small change that could really improve that sort of thing would be if you just have -1 for the offset, and define that semantic as read at the end of the previous read, then you can actually spam a whole bunch of reads, get back the responses, and get a lot of...
Yeah, and what you effectively described there is the next level for an abstract computer science theorist to take and expand the concept.
Yep.
Once you go back and you compare the two, write a paper about why the architecture going one way
Yep.
versus the other is better at the trade-offs, and that was what it was for.
Sure. As I said, it was a research system.
Can you repeat some of those comments?
Okay. So the comment was basically that Plan9 was designed more or less as a research system, where practicality did take kind of a second seat. I'm paraphrasing. Feel free to correct me if I'm going off the rails. And basically, so many of the improvements that came in, although I'd say they're surprisingly practical, were kind of there as a comparison with the existing way of doing things and a way to write papers rather than as a way to, well, improve the system in a fundamentally,
So
or at least the primary purpose.
we'll take one more question if there's...
What's the funnest and most intensive, computer-intensive thing you've done?
Writing my own language. What is the most fun and most compute-intensive thing I've done on Plan9? I maintain my own programming language for fun because, again, I said there was something wrong with me right at the start of the presentation.
What's it called?
Myrdin. MYRDDIN. It's a natively compiled language that runs on a bunch of systems. No libc, and one of the systems it runs on is Plan9. So it's actually usable enough that I'm using it at work for a few things.
Do you know what Captain Proto is?
Yes.
Do you think it could be used to augment 9p?
There are many things that could be used to augment 9p. The main thing is not that you have 9p, it's that you have one way of doing RPCs. And that's really the thing that you can't do on other systems, on systems other than Plan9, because you have everything else and you can't break a map, for example. Or you can't break sockets. Or you can't break, I don't know, give me another thing that people tend to use on these things. User space. Yeah, you can't break user space. And cutting everything down to a single way of talking with the entire system is going to break everything.
Okay, so Ori's going to be around if you have other questions. Please, round of applause. Thank you. So, next up we have a talk on scaling. As computing deployments get larger and larger, new and novel techniques are needed to create and manage infrastructure and the applications that run on them. Evolute has some ideas of how we can do this better, and we have their founder and tech lead here to tell us a bit about how to do it with Layer 7, which at this point I was going to make a joke about Layer 7 cookies here, but Deadpool told me that's not funny on at least 2 layers. Please give a warm welcome to Christopher Francisco and his talk, Scaling Infrastructure with Layer 7.
Well, right off the bat, I just want to say thank you guys for having me here, and unfortunately, this won't be as interesting as that was. I think just the history of that, just the beauty of it. I mean, no, quite honestly, that was quite amazing. So, my hope today is really to give you guys just a different way of thinking about infrastructure, and I think that some of what we're going to talk about is commonplace for such a technical audience, but other things are going to be, I would say, novel in the sense of how they're applied. Getting set up here, guys. Of how they're applied in an enterprise infrastructure environment. And so, just to give you guys a little bit of background about myself, I actually led cloud architecture at Apple for some time. Did some cool block projects, so on and so forth. I'm also a contributor to open source, but not quite so deep. One of the core 8 commands in that crappy old Docker ecosystem, I contributed to that. And so everything from the Mesos and Kubernetes environment, we've done contributions. And so again, I really wanted to give this talk on layer 7 infrastructure, and it's really talking about the evolution of not only quote unquote new but old technologies. Thank you, Rob, for calling container technology old. It is getting there. But I would say that from a quote unquote cloud infrastructure standpoint, it's still one of the latest technologies. And I think that as it gets more mature in our spaces, it's still having a pretty big impact. So guys, I tend to not be as long-winded, so I may have us out here sooner rather than later, but I want to take us through a little bit of an evolution to just kind of set the stage. And in what we started to see back in 2012 was that we really had this whole mindset of DevOps. I think we still have some people who have the title DevOps that are here. That's always the wrong thing to do, but we started to see this take on industry direction. And you know, I think one of the big things that happened around this time was that Google started to leverage real-time data to determine next hops in their BGP protocols. And so instead of looking at, okay, what is next from a distance standpoint, it was actually what is the fastest path around the world. And using that type of real-time data became a construct for how it actually delivered infrastructure. And so you started to see this continue throughout the ecosystem. Software-defined data center started to attack the all control plane functions, compute, network, storage, so on and so forth. We got desired configuration management, Puppet and Chef, kind of about around that 2015. And then today we're starting to see this whole rise of microservices. And very obviously, this is a quote-unquote all new term technology, but we're starting to see that very much ingenuity where we expect resiliency and intelligence at the protocol layer even built into our core infrastructure capabilities. And so everything's moving up a layer. We're starting to see intelligent routing, and that's always been there, but we're starting to see that done at more of a software layer. And you're starting to see, again, everything is just moving up a stack. And so we want to explore this topic of layer 7 infrastructure. So go ahead, Rob. No, I'm talking about, so you're generally data and control plane are kind of how you can separate things. We're starting to see that for the behaviors that we would expect, things such as, simple as, communication on using TCP ports, right? That kind of becoming a first-class citizen. I actually am not a big fan of that, but again, you're starting to see that we're typically going as far up to application level functions for infrastructure, core infrastructure services happen. And so it's manifesting itself in a lot of different ways. So my goal really is to really talk about some of the technical advancements in containers, to really dive into some of the methodologies which have brought success into the ecosystem. And some of this I tend to talk about a bit abstractly. You're going to have to pardon me because actually my system here failed recently, so I don't have the cool demonstration to show you guys. But what's really happening is that we're actually taking some new approaches to how we actually implement everything from namespace isolation, resource isolation, process isolation in a container environment, and it's creating new advancements in infrastructure. And so what we want to do is dive a little bit deeper into, okay, how is it that you can take those constructs and do new things? So one of the things we talked, which was mentioned, was kind of IoT. We started to talk about edge computing. Well, what is it that we can apply LXC and namespace concepts at that layer to then distribute software and, again, have more intelligence in our infrastructure. And so really diving into the core capabilities, and sorry, you guys, I tend to work with a lot of big systems and a lot of big companies, and so I tend to talk at a very abstract level, but the point is that we're going to really start to talk about what are the implications of this? What does this mean in actual business practicality and what that means for the environment? So whenever we look at this space and we look at container technology, we actually look at it from two different perspectives, and that's the technology and the business perspective. So we talk a lot about maturity, and maturity with the technology. I'm sure everyone here has touched a container. How many are just generally running it in production? Good, good. No, this is great. You know, from an industry's perspective, we probably are still sub 10% adoption in a production environment. And to say that it is pretty useful, I may end up fighting you on that. It still hasn't received widespread adoption, and I think there are some things that suck about it. But I think that it's 50% because we are applying the technology wrong, and it's 50% because we're not actually evolving the implementation for the purpose of what it's used for. And so at the core of it, the first thing you need to understand is what are you doing? Are you simply trying to get a smaller unit of isolation? Are you trying to actually deploy software in a very streamlined way? Or are you trying to have this very level of advancement in how you ebb and flow with software microservices? We see that kind of movement from pets to herds, heterogeneous software, as in I don't control my software environment, to homogeneous software. I create the software myself. And so we really start to we break down these capabilities across availability, portability, distribution, and control. And these are things that, even from a product standpoint, but more so an architecture standpoint, we look at, right? We want to understand what is it that we're achieving and ensure that the technology meets those capabilities. So everything from ensuring that an application is up within 30 seconds to ensuring that we can do entire services. We do distribution. I think we've gotten tens of thousands of Hadoop nodes up in sub 90 second time frames. So there is a lot of power behind the capability. And so we really do want to focus on how is it that we achieve the maturity based on the technology implication and the architecture. So what are the challenges? And you guys are going to pardon me because I'm going to grab my water. There's 3 core challenges, and one of the big things, and I'm sorry I didn't catch your name. Gordon?
Ori.
O-R-I. Ori. One of the big things Ori talked about was uniformity across objects in a much more technical way. I think that when we start to look at containers, namespaces are great once again, but when we start to look at the uniformity of that across any type of infrastructure component, this is a challenge because we tend to get this from 10 different places, from 10 different vendors, and it really isn't very simple to use in the ecosystem. Repeatability of how we deploy software and infrastructure. This is also a very big challenge because not only do we not standardize from a protocol layer, which protocol should be standard, we don't standardize from even just a technology layer. So again, there's a lot of cooks in the kitchen when it comes to the container technology. And that last area is function and access consistency. And so what we'll start to find out is that if we have a process for which we create any type of infrastructure component, the functions that we can perform against that become quite amazing. And that's everything from how you parse a language, old or new, down to the things that you can take from that. So when we start to look at an infrastructure component, there's just core things that we look at in terms of achieving the repeatability of object and data uniformity across the environment. So we're going to look at everything from addressability and naming to how we access that component in the actual protocol. And the point is to think about how structured this can be across any component. We'll dive a little bit more into that detail, but if you can put into a framework for which you access any particular storage, network, compute, any particular security negotiation, or how you actually look at an application. We tend to look at applications as being very different across systems, but they all have to comply to the OSI standard. So the point being is that if we can look at all of these constructs and we can create repeatable patterns, there's so much more that we can do with it. And so some of the things that we've been able to enable is things like failure detection and response across any layer. So anything from a storage device failing to an application failing across host, network, the local system, the actual container, we can actually detect that and respond to it based on object and data uniformity. And so really being able to streamline major software capabilities and what we consider kind of a zero configuration way. So if you think about the ability to, once again, have this type of uniformity, it means that you no longer worry about core configuration. You only worry about the ability to deploy or scale that capability. And so it starts to get to a place where there's very little configuration involved, and this kind of zero conf approach to infrastructure becomes possible. So, you know, in a very terse example, if we have a web a DB instance that's out there, because we understand every bit of its access protocol, addressability, naming, we are able to very quickly establish anything from security, central layer routing, anything that we want to do with those two application components or services, we can do that because we already have a structure for which we're communicating across any application. So some more detailed ways to look at that is, for example, resolving configuration. Whenever you look at an application and its deployment, it's either going to be dynamic variables of which you're coming across or static variables. You may call them many different things. They may be in many different places, but they really only change so much. And so, again, when we start to look at that uniformity, let's say that we're looking at the configuration for how we are actually going to resolve our DNS server or our remote service. We can simply, based on this very structured approach, understand the addressability of the protocol that's being used, whether that's you know, DNS, HTTP, or we're resolving, we could be resolving names, we could be resolving configuration. That again can be via many protocols. In the way in which we access it is going to be protocol specific. You know, the container is probably a more native example. If we know that we have a structure for naming our applications addressability, the protocol which is being used, OCI, which is a standard, but there's very many implementations that adhere to it. And the way we access that, if we have all of that laid out and structured in a format from the beginning, it actually makes everything else super simple. And so again, this kind of way that you structure your software, structure your environment, becomes a way to normalize it in a way to achieve higher order patterns. So one of the things that, and I just have to reference your presentation because you beat up on all the great things that's happening with containers. You know, one of the things that you don't see often, and one of the things that we did at one of our past presentations here, is we showed software moving from different environments. And we've gone, it's been as poor as us taking POSIX compliant containers on a Solaris zones and ZFS based environment and moving software across to a native Linux and x86 based environment. It's gotten that bad in the world. But I think in our previous demonstrations, we took things like as crazy as Oracle database, and we took that from any previous environment and moved that into a container. And again, if you understand the functions for which we're trying to do this for, there's value there, right? Especially in large companies, because you really want to be able to have that uniformity across your ecosystem. And so when we start to look at, we've actually been able to make several iterations on this. And when we start to look at doing any, we've actually been able to take places where you have multiple applications on a single system, completely move them across software platforms, across cloud environments, break them up and allow them to communicate based on that environment. And while there's, for the latter 10% out there, there's still some work to be done. Microsoft's big thing was, surely you haven't figured out the network piece, and we've been able to do that architecturally and do some implementations there. But the point becomes is that the idea of allowing software to achieve its most scalable pattern in a single execution is quite big. This framework, it's quite proprietary. We had one of our vendors on site at a Fortune 5 here recently, and they were like, how do you do that? And they were taking notes. So please take no pictures here. But we really started to come up with binary configuration data. And if you start to think about, again, what's dynamic, what can be predicted, what is structured, what is unstructured, any construct really falls, any software construct really falls into this, one of these core 3 categories for us. And so if we can dissect hundreds of variables across any of that application, we can basically place them into these buckets and move them across any bit of software architectural network distances. And it really does become for a powerful way to achieve what I'm going to call native containerization and or a simple operational platform at scale. So again, we start to talk about repeatable patterns, and when you start to really look at those repeatable patterns, this is the type of things that it enables. So the last kind of architectural challenge that we've been able to generally overcome is what we call that function access consistency. And you know, I had a talk with one of the cool guys at Apple here recently, and I said, you know, the programming language that's being used in any environment, it actually tells us a lot about how the software is going to behave. Yes, we can do, I mean, there are so many things you can do, right, in any programming language. But the fact of the matter is that down to the libraries and function calls that it's making, it informs us a lot about the capabilities, about how it's communicating, what it's communicating. And so the point being is that because we can tap into the insights of that, we're actually able to achieve things like being able to detect where failures occur, whether that be TCP-based, network-based, or even lower down the stack. Is there you know, memory dumps? What's happening in the environment enough so that we can see enough to do enough with that actual software? And so it's really provided for a powerful framework to achieve just, again, this whole mindset of not having to do a lot to parse an application in order to achieve scale, distribution, and many different things. So back to our first slide where we talked about this framework, availability, distribution, control, and portability. These are the things that we look at across cloud, edge, and migration to ensure that we achieve scale. So in the cloud environment where we may focus on, I kind of look at this a little bit like CAP theorem in the sense of, you know, in any application, you're only looking at 1 to 2 specific core areas that matter in that environment. And so if you once again approach it by trying to pay attention to everything, you tend to lose the value. But if you look at it from the standpoint of, okay, what is the core of what I'm trying to achieve in a specific layer, like the operating system layer? The reason that we've been able to take software that's native on an L4 microkernel, even though it's POSIX compliant, and move that across platforms and operating systems, is because we focus on the distribution piece there. You know, improving the portability, and I'm embarrassed to say this here, so you guys will have to mind me. We were talking with Microsoft CTO here recently, and we do deal with enterprise environments, so we have to work with those other operating systems like Windows. And it's just a true statement. And they said, well, surely you can't containerize a desktop application, right? And it's because obviously you can't get graphical input into quote unquote containers, right? And some people have tried to do that, completely wrong way to do it. But we've been able to do that because of how we implement our namespace constructs in the Windows environment. And so again, our passion is not for, unfortunately, a specific way to do things in a specific operating system. It's for the maturity of the software for the constructs that we're doing it in. And so that replicates itself across migration. Again, we want to increase distribution. If you can essentially take software from any single location and move that to any other location, in literally under 3 minutes is the average time we take. you start to see some crazy things, like if you want to use free tiers across AWS, GKE, and Azure, and just allow your software to distribute itself anywhere. It's kind of easy to do. Now, that's just a terse example of it, but the point is that, you know, software should be able to be anywhere. It should be able to be ran with anything and generally in any place that serves it best. And so, again, very granular portability in achieving that native containerization. In this last area, which is the edge, we've actually been able to do some really cool things here. So how many people have actually dealt in edge computing? Okay, we got a few. Good, thank you. So, you know, network distances become some of the biggest difficulties when you start to look at that arena. And the fact of the matter is that when you look at software distribution, you look at the operations of edge, you have a lot of distributed control that's out there, and you don't always have access to it. And so the fact of the matter is that it's a lot like this, right? You really want to be able to push updates if they're 0 day. Unfortunately, these things don't kind of get 0 day as far as I know. You want to push that there, right, and make sure that it's secure. And you want to be able to have that software just be able to be controlled and distributed at will. And the cool thing, and this is kind of in theme, is that when you look at, you know, LXC commit, you look at how we tend to almost have a block level consistency, right? Whenever we iterate on an application image, the ability to continuously deploy that and achieve that across your software applications becomes very powerful in the edge environment. So that ability to, again, distribute and then control that distribution, as in when the actual instantiation or operations of that happens, is very powerful. And so again, even though we're focusing on distribution and control there, it shows if you're using your containers in the right way, in the right places, at the right time, how powerful that can be for infrastructure. So guys, I told you I'm going to be quick, and we're nearing the end of this very terse presentation. But some of the things that we've been able to see from this framework is things like having a layer 3 namespace across multiple operating systems. Now, I don't know about you guys, but if you've ever tried to achieve in containers having the same namespace that is native, you're not doing that NAT crap, right? It is awful. But the idea of having anything like you know, BGP at the host informing your ARP layer enough to have that happening across multiple operating systems and have those operating systems act cohesively for the software that they're working towards. We actually just showed that capability to one of the big network vendors who are now incorporating it into their environment. So the point is that, you know, the maturity of the container construct comes from being able to have that object and data uniformity. Again, we talked about you know, even having server and desktop applications be represented in a single service. It's kind of unheard of, but because we have that consistency, or I should say that uniformity, we're able to do that. Repeatability and item potency, again, the ability to move applications. We've actually been able to automatically migrate, again, applications in other software environments. So it's a little terse, but it's almost beautiful when you can see something as ugly as a drilling application that may be Windows-based, right? Automatically containerize itself. I mean, it's kind of sick, but the point is that, you know, we have this policy of, you know, no container left behind. If we can achieve this level of maturity with the technology, then what's really holding us back? And the idea is that, you know, we don't get stuck where you have beautiful technology that's not making it to the next generation, and we're able to achieve that at scale. And so, you know, again, because we look at the repeatable deployments, we want to be able to have a single place to be able to control objects anywhere. And so whether that be in the cloud or at the edge or whatever that is, the point is that we have because we have a single construct for no matter what the application is, we can control it all uniformly, no matter where it is. And so this becomes, again, a very powerful thing in larger environments. So this last area is kind of that function and access consistency, and we talked a little bit about the distribution. I think that that's probably one of the things that's really striking a lot of people, in that the idea to now treat software as you in the enterprise as you do a mobile device is a pretty interesting way to look at things, and we've been able to show that containers is that best construct to achieve that level of scale. And again, centrally defining, being able to be powerful enough to allow others to actually control their operations is possible because the central definition that containers have, we all know about the desired configuration management or Docker file type of approach. You can achieve that in multiple ways in any environment, but also the systems nature of it is able to be decentralized, and it's also able to give operational instruction. And so, of course, we've added a lot of things to make that more possible, but the point is that we can achieve that level of function and access consistency. So, at the end of the day, this boils down to, can we get 200 to 400% reduction in cost by achieving the density for our compute environment? Are we able to scale software beyond our needs? I know that one of the things I alluded to earlier was there was you guys have heard this back in the early Mac days, that Mr. Jobs said, "Hey guys, let's get this boot time a lot faster." And the engineer replied and said, "What does 20 seconds do for right?" And he said, if you take all the systems that we have out there, we could go to the moon and back based on the amount of time. And as we look at the ecosystem, it's kind of that way. Why are we still pillaging on 3 to 5 minute boot times? Why are we still out there running our software on very monolithic hypervisor layers? And the point being is that if we truly want to achieve that level of distribution scale, we have to be able to leverage a construct that allows us to do that. And because we're able to deploy faster, because we're able to respond faster, the agility piece is there. And I think that it's very difficult to even see that that's possible if you don't have any uniformity with your application of software. But the moment that you do, you start to just allow for the software to almost control itself, and it's just kind of a beautiful thing when you start to get to that level of maturity. So I'm gonna beat myself up because it's one thing to talk about this, but it's another thing to show this. And I am not going to be a sales guy, but Rob has been beating me up and saying, "Christopher, you need to be a sales guy." So I will say this, if any of you guys want to actually see this type of thing in action, I will not sell you, I will just show it to you. But the point is that, if we're really looking at kind of this next generation of infrastructure, we really have to start thinking about what are the programmatic and functional capabilities that we can achieve with any protocol based on maturity of the actual environment. And so I encourage you to re-explore, if you haven't explored already enough, the level of scale and capability that you can achieve with the container technology. Obviously, we have impacts that we can be there, but what we're finding is that the ability to take infrastructure to the next layer becomes possible with these types of constructs. And so thank you for your time. Yeah, I know. One of the coolest things I like to show is so we'll move something like as crappy as like a Cassandra database. Because it's in the platform, it'll automatically discover its seed, its peers, and it will just exist in the container environment. And it's kind of cool, but I can show you that, and that's the kind of general demonstration I like to do.
Who do you consider your competitors? Everybody's
our competitor. Plan9 is our competitor. So we were on site with this is being recorded. Okay. Oh! There was a really big company that just went public recently on site, and they said, you know, so we do this move and run thing, right? We believe that every application should be represented in a container, so we allow this move piece. But we also do this really cool run piece that we kind of don't tell people because it's so damn competitive, right? And so when it came to the run piece, they actually said, you know, we took a piece of software, again, that wasn't traditionally able to be in a container environment, and they said, well, they want to take that software and run it in that platform. And what they recognized was that because they were taking the quote-unquote hypervisor approach, they couldn't do it. And you know, that's kind of where we say, hey, we're happy to help. So again, I think that unfortunately, you know, a lot of people have been our competitors. But I think that we don't look at it that way, actually. If there's nothing that you get from this talk but the idea that we believe containers should be used everywhere, I think we have more thought competitors than actual competitors. So, you know, we can do this in a very Kubernetes native way, in the way that we do it, so we can be compatible with that type of environment. Same thing is true at Mesosphere, even though I don't like to tell people that. And the point is that, you know, I think our competition is the people who don't believe that organizations can achieve a better level of scale, even if a single application isn't getting a microservices capability out of it. We can still achieve better scale if we have uniformity across how we do infrastructure. And so I think there's plenty of people who buy into that. Hopefully you can think of them, and those are our competitors.
You quantified your cost reduction by 6 dB. You said, you know, half or a quarter, but then you said scale. So you're talking about scaling like, you know, 3 dB or 10 dB. So like 10 times or 100 times, or you know, you quantified your price reduction. How about the numbers? And you said boot time down to a minute from X number of minutes.
So we've shown Oracle database with data in 30 seconds. So, you know, I think that...
They need help. Oracle definitely wants to fight with the others.
Fair. I mean, but the point is that you're looking at it from a standpoint of cost and scale. They're kind of separate things, right? In just the 1,000 megahertz less overhead for rerunning the operating system, 100 megabytes of just core hypervisor overhead is enough cost savings, right? Or enough density enablement to allow for cost savings. We should talk about agility. You know, software deployment actually, surprisingly, is probably like the top 3 spaces for enterprise companies. So as Intel calls it, they say, you know, people want software at the rate of which they ask for it. And so the idea that you could, you know, say, give me an entire drilling platform and just be able to deploy that, right? Give me an entire, I don't know, give me an entire, you know, telecom POP, right? And just be able to deploy that is a little unprecedented, but that's the kind of capabilities that we're talking about.
Especially since it's all virtualized, and then the reality underneath it kind of still painful for most.
That's true. Yes. Yes.
Does this infrastructure like take arbitrarily current written code and support it? So I could take an existing Python microservice and scale it up?
Yes. Yes, it does. Embarrassingly, yes. You know, we were talking to the founder of Sensu here this week, and he said, you know, we got this new release coming out, but you know, the old release is all Ruby based. And I was like, yep, that's the kind of stuff that we love. Because the fact of the matter is that, you know, not everybody's going to be ready, you know this, right, to just, you know, re-implement that entire piece of code. But the idea of being able to spin it up multiple times, being able to segregate its data in a way that allows multiple people to use it, it kind of becomes a cool way to scale a piece of software. And, you know, maybe it is that you're going to actually rewrite that, but we don't believe that because you're not doing it just yet doesn't mean that it shouldn't be able to scale or achieve some level of maturity.
I think they're your typical Docker images.
So this is really cool. So we used to be a lot bigger. I forget. Oh, Mr. President over there beat me up on this last time. We completely changed our architecture because how much he beat us up. So Yeah, thank you. The best way to put it is that, you know, we're line rate, and that's going to sound awful. So before, we actually used to take everything that was a part of the system, right? We wanted to make sure that all the libraries were there. We wanted to make sure that everything was there. Now, we've actually, back to binary configuration data, we're able to parse every bit of the operating system, the storage, the network environment, to essentially bucketize every bit of component of it. And so because of that, we don't need anything from the system layer, quote unquote, except for if it's specific to your application, right? And so in that regard, your application, not only will it perform just as it had done, the previous architecture did that, but it will actually be the same size as the application was in its previous environment.
Well, that actually raises my next question, would be, is considering you have a program A, and most of the time when you run it, it actually doesn't access certain resources, but once in a blue moon it does. Clearly, if you have run it a few times and created a profile, this would be considered a fault then, because it would effectively need to fetch the missing data. So my question would be more of, does this process that we're splitting up binary configuration data also then have cases of, oh, it did not figure out, it underbid, it, for example, made it too small, and now has to actually fetch the missing piece and compare it? I find this in my Docker applications for Python, because I still got all the ones that have not been touched by the current process. But sometimes I get surprised because there are conditional imports that may or may not touch it, and also may have erroneous imports that aren't used either.
I get where you're coming from. Here's the thing: that application in its functioning state, all the libraries that it references are a part of it, right? So unless you're adding code, right, it's not going to go and fetch things that you may not be using, right? But because your program expresses itself, it tells us what libraries it's using. It tells us the software environment. So from that standpoint, the things that it fetches is external to it, but the things that it uses to fetch it is internal to it. And so if there's a specific configuration, that means that there's a one-off, right, of it needs to fetch this sometimes. That's a more dynamic variable. But the things that the actual application consists of, it's always going to be there.
Is this actually does this have a defined path for handling this dynamic case?
So yes. Yes. Yeah. Okay. Yep. Yeah. So that was long story short is yes. Yep.
So, maybe like 15 years ago, there was a presentation, some company called fast something, but they could take a running Linux application, let's say Apache, right? They could profile it, and they could take just the kernel bits that it was using, just the processes and files that it was using, those libraries, and give you a small slice, and spin up that slice.
So you're abstract.
Right, exactly.
It's a bit difficult.
Very similar sounding tech, right? I'm not sure if that's...
No, it resonates a lot, and I think that so to us first and foremost, there's a lot of intricacies with the capability, and the reason we provided that is because if you have to do that over 500 applications, you're just going to give up. So the reason that you don't think about doing containers at scale is because you're like, holy shit, that's a lot. That's a lot to do. So I think first and foremost, I think it is similar, but to us it's a means to an end. And I think when you understand your software on that level, there's so much more that you can do with it, right? So now that we understand not only the software environment, we understand the infrastructure environment. I mean, again, the level of distribution, portability, access, scale that we can now do with it is the intent. And so, yes, we do some very novel things there. I think I consider us still a leader in that space, even though there's people who have copied a little bit. I don't think we're trying to innovate there in the sense of we want the scale to occur. So obviously you go through this level of microservices shift. We don't argue microservices. I believe that's a design pattern, right? But we do argue that your software will be able to achieve the same level of distribution, therefore be able to scale to that level. So again, it's a means to an end, right? And I think that's the focus.
Do you have a particular containerization model that you use that's unique, or is it based on Docker or whatever else?
Mhm.
There's a big difference in how you handle an application.
We believe in being extremely open. So it's possible to bring it into a Docker container, a native LXC, and the reason that we talk about those different formats is because again, it's technically, and this is very hard to say because it's not true programmatically, but it is true in the real world. Is that it's technically just another format to us, right? And so we want to treat it that way. Not because we don't think there's a better way to do it, in which we do have our own implications for what should be done at a container level, but we do want to stay true to the goal, which is just to get you there, right? So that's important.
Thanks. Awesome.
All right.
Any more questions?
I don't have a question, just a question, it's a comment. I think this was fun, the list of BayLISA talks that I've been doing a long time. From Plan9 to Evolute, I'm just like, we just spanned.
I was thinking the same thing.
Awesome, so I want to say thank you to you both.
Thank you. Thank you.
And thank you all for coming. We're here every month, as we said. Next month, we have a talk from Mesosphere folks on their new release of DCOS. So you should come for that. I believe there's still pizza and drinks outside. You don't have to leave just yet. And Ori and Christopher are here to answer questions if you have any left. Okay. Thank you again for coming, and hopefully see you again next month.